Now we're going to solve rational inequalities. This is a 6-step process here, which will be easier to see by example, but I just wanted to make sure that you saw this in writing in case you want to write this down and refer to it in your notes. First thing we're going to do is take an inequality and turn it into an equation just by replacing the inequality sign with an equal sign. We'll find the least common denominator, multiply through by the least common denominator, and solve it like normal. Once we do that, we're going to find not only the solutions that we have, but any number that causes a division by zero error. And we're going to take these points, put them on a number line, and see which regions will make the inequality a true statement. Again, this is much easier to see by example. So let's solve the inequality 1 over 3s plus 2 over 9s is less than 2/3. First thing we're going to do is turn that inequality sign into an equal sign. So now we have the same statement equals 2/3. Next thing we need to do is find our common denominator and multiply through by it. Now usually you'd want to factor here. This is going to be 3 times s. This is 3 times 3 times s. This is 3. So and when it's a simpler problem like this, sometimes it's just easier to look at it and realize that your least common denominator is going to be 9s. Because 9s is the largest term and everything else goes into it. So we're going to multiply through by 9s. Take our first term here, times a 9s. We'll just put it over 1 because we're multiplying by a fraction here. Same thing, 2 over 9s times 9s. And finally, equals 2/3 times 9s. This is where we have our opportunity to cancel things out. So let's take this here. We have an s on the top and the bottom in this term. We also see a 9 over 3, so that cancels down to simply having a 3 in our numerator. Over here we have a 9s and a 9s. I'm just going to cross the whole thing out. And on this side we have a 3 and a 9, so I can simplify that down to just be a 3, and we keep our s there. And once we do this, we're left with 1 times 3, or 3, plus 2. Everything else is gone, so 3 plus 2. Starting to like the sound of this. And on this side, 2 times 3 times s, or 6s. Well, we know that 2 plus 3, hopefully, is 5. And then we divide both sides by 6, so that s equals 5/6. Now, this is what I was talking about with that extra step. Once we solve it like normal, then we have to find the dividing by zero errors and add it to the list of critical points that we need to check. So 5/6 is already automatically one of our critical points because it's our solution. The only other thing that can cause a denominator to go to 0 here is when s is equal to 0 itself. So that would cause this term and this term to both go to 0. So our critical points are 5/6 and 0. Go ahead and show you that here. Then we need to make ourselves a number line that has 0 and 5/6 on it, and we need to see if each of these regions is going to make this inequality come true. So now we're done with doing the equation. We're back to the original inequality. For when I'm doing this, I like to pick very easy numbers that fit in each of these regions. So some number smaller than 0, pretty easy one, is going to be -1. Something larger than 5/6, an easy number is +1, because 1 is always easy to multiply by. And something between 0 and 5/6, I picked 1/2. You can kind of pick anything in that range there. And then I plug each of these into the original equation to see what would happen. So if we take a -1 and plug it into this equation, we're going to have 1 over 3 times -1. We're going to have 2 over 9 times -1. And we're going to have that being less than 2/3. Go ahead and simplify this down. And I'm actually going to skip the work part of it, but you would want to get yourself a common denominator of 9 in both of these. So multiply top and bottom of this by 3. Get a negative 3/9 and a negative 2/9, which is going to give you negative 5/9. And that's all less than 2/3. Well, a negative number of any kind is going to be less than a positive number of any kind, so we know that this is a true statement, which means that we can shade in this area of our number line. We repeat the same process here. We're just going to plug in that 1/2. So we're going to have 1 over 3 times 1/2 plus 2 over 9 times 1/2 is all less than 2/3. If we crunch the numbers, on the left side we're going to get 10/9. Now again, this is something you could do in your calculator if you wanted, or you could just get yourself a common denominator and add the two fractions together. But you're going to get 10/9 on the left is less than 2/3. Well, since 10/9 is greater than 1 and 2/3 is less than 1, we know that that is not true. In fact, we're telling dirty lies here, and we will not allow that, so we will not shade this region of the graph. Finally, let's plug in 1. If we do that, we have 1/3 plus 2/9 less than 2/3, and if we simplify that, it's going to give us 5/9 is less than 2/3 if you do out the math. 5/9 is equivalent, 2/3 here, if we want to get ourselves a common denominator for comparison's sake, is going to be equivalent to 6/9 if we multiply top and bottom by 3. And 6/9 is greater than 5/9. That is true, and we uncover that part of the number line that we would shade. So again, going back through what we did here, took the original inequality, turned it into an equation, and solved it. That was one of our critical points. We figured out what things cause the denominator to go to 0. That was our other critical point. Put those numbers on a number line, and between each region, we tested a point to see what type of value it would give us, whether it would make the original inequality true or not. Then we shaded the number line, and if you're going to write your final answer for this, you would simply write it as s, or well, in this case x, less than 0, or your variable is greater than 5/6. So let's do another example here. 1 over x plus 3 over 5x is greater than 2/5. First thing is we make it an equation. So we drop that greater than sign and turn it into an equal sign because we want to figure out one of our critical points. At this level, we need to find our common denominator, least common denominator. I see an x, a 5, and a 5. My least common denominator is going to be the lowest powers of each of those, so 5 to the first times x to the first, or 5x. I can agree that everything here is going to go into 5x. So let's take each of our original terms and multiply by that 5x. And when we do that, we get to our canceling step. See an x in the denominator, x in the numerator, cross those out. A whole 5x that cancels out here, and a 5 that cancels out here. Which leaves us with only 5, because it's 1 times 5 over 1, so just a simple 5, plus, everything's gone here except this 3, so 5 plus 3, equals 2, and don't forget that x over there. We have 2x all over 1, so equals 2x. We combine this side, we have 2x equal to 8, and then divide both sides by 2, and x is equal to 4. So one of our critical points is 4. The other one we find by looking at our denominators. What causes either of these to go to 0? Well, only x equals 0 can do that. So we know that our other critical point is going to be x equals 0. I'm going to highlight these here so that we know where our critical points came from. One from dividing by 0, and the other one in this case came from solving our equation. There's nothing that says there couldn't be multiple solutions when you solve this, if you ended up with a quadratic or something else. There's also nothing to say that you couldn't have multiple critical points when you're checking for your divide by zeros. So it's just in these examples that we've done, we've happened to have one of each of them, but there could be any number. So when we know our critical points are 0 and 4, we put it on a number line. And we have to test each region. We're finding easy numbers to work with. Again, I know that -1 is easy to work with. +1 is easy to work with. And on this end, it's kind of arbitrary. I chose 5 because it was the next integer. But you could have just as easily taken 10 or some other number. And you pop them into your original equation. So we're going to put this -1 in for x and see if this is true or not. Let's put that in here. We have a 1 over -1 plus a 3 over 5 times -1 greater than 2/5. This term is going to go to -1. This is going to go to -3/5. So all in all, this is going to be -8/5 on the one side. You can use your calculator or find yourself a common denominator to work with that. Your 8/5, -8/5 is greater than 2/5. Well, a negative number is never greater than a positive number, so we know that this is simply not true, which means that we do not shade this part of the graph. Let's try it with a +1. Same idea. We plug in our +1 down where we had an x here, in both places for an x, and test it out to see if this equation is going to work. You can tell the numbers are going to be pretty similar here. We'll have 5/5 plus 3/5 is 8/5, positive 8/5 this time, greater than 2/5. I think that 8/5 is in fact greater than 2/5. Therefore, this is true, and we do shade the middle region. Last one to check is our far right region, anything greater than 4. So we're using the test point of 5. Plug in a 5, we'll have 1 over 5 plus 3 over 5 times 5 is greater than 2/5. This is 3/25. 1/5 is 5/25, so it would be 8/25 on the left side. It's greater than 2/5. Now we aren't comparing apples to apples here, so if you want to get yourself a common denominator to compare, multiply top and bottom by 5, and you would end up with 10/25. 10/25 is not less than 8/25, so this is not true, and we do not shade the far right of this graph. So the way that you would write this answer is x is between 0 and 4. Again, our number line also says the same statement. Quick recap. I'm going to go back to our instructions page here. We take the inequality and write the equivalent equation so that we have an equation here with an equal sign. We find the least common denominator and we multiply through by that. So in this case, our least common denominator was 5x, and we multiplied every term by 5x. We then solved the equation just doing standard algebra until we got our value of x or s or whatever our variable was. Then we found our additional critical points by seeing when we could divide by 0. We looked at the denominators here and we saw that adding or multiplying by a 0 would cause each of these denominators to go to 0. So that was our additional critical point. Then we put them on a number line and we checked each region with a test point to see if it worked. We shaded those regions in if they did work in fact, and then we're able to write our final answer as an inequality statement.